In this video, we are going to talk about the implementation in DIgSILENT of one of the most famous algorithms in history, which is the Fourier transform. Actually, we are going to talk about the implementation of discrete Fourier transform, which is a very important algorithm used in image compression, audio compression, signal processing, approximating derivatives, so on and so forth. Actually, Fourier transform is a way of decomposing a signal into sinusoidal waves. The core of this transformation is this equation. So for continuous signal, we have the integral from minus infinity to infinite of a function, of our continuous function, multiply with a analyzing function, which contains sinusoids. As you can see, this last part, the analyzing function, resembles with the Euler equation, as you can see it here. This is one of the most important equation in mathematics. So e to the power of ix is equal to cos x plus I sin x. So you see we have here a cosine for the real part, and the sine in the imaginary part. Okay, so this is for continuous signals. Because in the industry, in the technology, we do not use continuous signals. We use discrete finite data. This equation transforms in this equation. So as you can see, we do not have the integral anymore. We have a sum. We have the sum of from n equals 0 to n minus 1 of the function multiply with the analyzing function. Writing this equation in the matricial form, as you can see here, the first term is xk. Yeah, the first term is the frequency component vector. Yeah. The second term is the discrete Fourier transform matrix, the analyzer function actually. This is depicted graphically. And the last term is actually the data vector, the discrete data vector. Yes. So as you can see, the frequency component, actually a frequency component is represent how much a frequency is contained in the signal. So a frequency component is just a multiplication of a sine and a cosine wave of the same frequency with their corresponding point from the data vector. Okay, so if we have the matricial form, let's see how this DFT matrix is computed. Based on this equation. As you can see, this matrix has this form in which omega is e to the power of minus 2pi divided by n being the length of the signal. Further, I'm going to show you how I implemented this algorithm in DIgSILENT. So here we have the script, discrete Fourier transform. Okay, so it's a very simple algorithm, which it has two steps. So first step is computing the DFT matrix. Yes, and the second step is multiply the DFT matrix with the signal. These are the steps that I previously showed you. So first step is computing this matrix for a certain signal size, and the second step is just multiplying DFT matrix with the signal, resulting the frequency component vector. Okay, you can see here that we have two matrices because DIgSILENT doesn't work with complex numbers. So because the values from the matrix, DFT matrix, are complex, I wrote two matrices, one for the real part of the DFT matrix and one for the imaginary part of DFT matrix. The real part of the DFT matrix we're going to put inside the real part of e to the power of minus 2pi divided by n. So with the real part, according to the, once again with the Euler equation, the real part is the cosinus, is the cosine. Yes, so it's cosine 2p, so on and so forth. And for the imaginary part, is the imaginary part, once again, is the imaginary part of e to the power of minus 2pi divided by n, and according to the Euler equation, is the sign. So because it's the minus 2, here in front of the sign, we're going to have minus. Let's see. So we have minus sine 2p, so on and so forth. The size being the size of the signal. And the second part, here just the multiplication of the real DFT matrix with the signal. DFT matrix with the signal, resulting the frequency component vector. Here also we are going to have two matrices, one for the real part and one for the imaginary part. Okay, so this is the algorithm. Further, we have just how we plotted the values. So the values are going to be plotted as a complex number, a, d, and also is going to be represented in the polar coordinates with magnitude and angle using these two equations. So for a complex number, the magnitude is going to be computed like this one, like this, and for the angle is arctangent of imaginary part divided by real part. Further, we are going to demonstrate the efficiency of our algorithm in DIgSILENT to the one from Matlab. So I wrote a script in Matlab, a very small script, in which we have the equation for a signal, which is going to be represented in a finite interval from 0 to 5 with discrete steps of 0.1. Yes? And this signal is going to be introduced in their dedicated fast Fourier transform algorithm, and we are going to obtain the frequency component vector. Yes. Let's execute the script. So this is the plot, the plot of the signal. We should obtain a plot similar to this. Okay. I'm going to close this. Now let's see the results. The results, as you can see, are putting this vector in y. As you can see, there are complex numbers, 50 complex numbers. Okay, so now we have the results in Matlab. Let's do the same thing in DIgSILENT. First of all, we are going to take the signal, the already computed signal from Matlab, which is stored here in X. We are going to copy the signal, Ctrl+C, and we are going to paste it in its corresponding matrix, in signal here. I already introduced the values. I'm going to paste them once again. Okay. Now, once we have the signal introduced, we will execute the script. We will obtain a similar, identical plot and also identical results. So execute. So you can see this is the plot. Actually, let's run it once again because I closed this. Yeah. So as you can see, the plot in DIgSILENT is identical with the one in Matlab. Furthermore, let's compare the results of our algorithm that we just created with the one dedicated from Matlab. So the values are put here in y vector. As you can see, the results are identically. As you can see, for the first frequency component, we have the real part 90.27. Here, the same results like the algorithm from Matlab 90.27. The imaginary part is 0, in our case, 0 in the case of Matlab. For the second component, we obtain also the same real part and imaginary part. You can see 15.42 for DIgSILENT and 15.42 in Matlab, and minus 13.53 with minus 13.53 in Matlab. Let's go to the last values to check them. As you can see, 15.42. So you can see we have also 15.42. So we have the same results like the algorithm from Matlab. And 13.53 with 13.53. So we obtain exactly the same results. One thing that we have here is the polar representation. As you can see, each complex number, its frequency, is written in terms of polar coordinates in magnitude and phase or angle, as you can see. Okay, that's it.